You should have already seen the kind of introduction play pause it video into Acetals, which, just for the record, is the least favorite play pause it video of all time. I've had a lot of people complain about it, and I kind of apologize for that, but that's where it is. So what we're talking about now should be some of the kind of missing pieces of that Acetal video because I didn't go into a whole lot of it. But to start off, we'll get a little bit of a warm up here if technology would work with me. Because you've now seen some acetals, you should be able to go through and identify whether the following things are a hydrate, a hemiacetal, an acetal, or none of the above. So take a second to pause and label that out. Now that you've got it labeled out, we can go through and mark these out. If we start our acetal shape, what we're looking for is a central carbon with two oxygens connected to it, and then those oxygens connected to carbons. The acetal itself is right there at that carbon. That's the primary characteristic. So if we go through, we've got a carbon with two oxygens with carbons. There's an acetal. We've got a carbon with two oxygens, but those oxygens are not connected to carbon, so that's not an acetal. We've got a carbon, two oxygens, and then more carbons, acetal. Carbon, note two oxygens again, but not both connected to carbon. And then the last one, I do have two oxygens connected out to multiple carbons, but there's not a central carbon connected to both oxygens. That is not an acetal. If we move through the rest of them, what do we have? A hemiacetal is next. Really shouldn't have erased all of that. Okay, the hemiacetal is starting to become an acetal, but not fully. One of those oxygens is connected out to a hydrogen. Okay, if we take a look, we're connected out to one hydrogen, but a second hydrogen, so not a hemiacetal. We move to the next one, hydrogen, carbon, there's a hemiacetal, and the last one didn't satisfy the conditions for an acetal, it's not going to satisfy the conditions for a hemiacetal. We could then move through to, hydrate. The hydrate is not an acetal, but it has a similar characteristics. We're now looking at that same central carbon, but now the oxygens have two hydrogens, so this would be a hydrate. And then the last one still doesn't fit that category, so the last one comes in as a none of the above. Okay? The next step after you've identified acetals is to push it a bit further and to kind of pull it apart and decide where those things came from. So what would be the partner for them? The partner, the corresponding partner, would be our carbonyls. So if we were to revert back to our carbonyl structure, what is it? So we know we need to go back to a carbonyl. That carbonyl is going to have the same characteristics of our acetal. That carbon, where the two oxygens are connected, is still the same. But those oxygens won't be connected, or those oxygen tails won't be connected. So what we're doing is deleting those bonds. The other bonds still stay there. Okay? The acetal portion of it, or the other kind of flip on it, or the remaining pieces, would now be our oxygens with the chain with only two carbons. And we'd have a second one with the chain. Those oxygens wouldn't be stable, so we'd throw in the H for our alcohol. The other acetal is a little bit trickier because when we go through to break this one apart, we know that that carbon is connected out to one other carbon, which is then connected, 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 connected. 1, 2, 3, 4, 5. Oxygen. 1, 2, 3, 4, 5. Oxygen, hydrogen, hydrogen. This is an interesting one because it's all self-contained. We're not bringing in new alcohols to the structure. They're already part of it. It's just a question of how they all linked together. And of course, that one gets to be a fun one on an exam because it wouldn't get written out that way. It would get written out in the chain 1, 2, 3, 4, 5, 6, 7. Make sure I did that right. 1, 2, 3, 4, 5, 6, 7. Cool. Ooh, that's supposed to be an arrow. 2, 4, 6, 7. At those positions, we have our alcohols. 1, 2, 3, 4, 5, 6, 7. Sorry for all the counting. 1, 2, 3, 4. 1, 2, 3, 4. At position 4, we have a carbon. There's our purple carbon and the carbonyl. And that's how you would see it on the exam. Okay? And actually, if we're going to do it on an exam, we'd have better bond angles, and we'd have that. Okay? So we're responsible for being able to move through those pieces. Okay? Those were interesting, kind of fun. So we've got 2 more examples that I would like you to do on your own. Again, if you've got questions about these and you aren't able to figure them out, then please contact me and we'll talk through those answers, but you should be able to nail those down. Okay? For the record, this one has 2 pieces. This one has 1 piece, if you were able to split those out. So these are indeed acetals, but if you split them into their carbonyl forms, you'd have one structure with all the alcohols or everything in it, and then the other one you have 2 structures, one with carbonyl and one with the alcohols. Okay, so you should be able to pull those apart and verify them for yourselves. Okay, so what we're looking at within this chapter, because this is now moving to chapter 18, is now our weak or weaker nucleophiles when it comes to nucleophilic addition. So this is looking primarily at oxygen and nitrogen as our nucleophiles. The oxygen, or a large part of this, becomes challenging because these are all very equilibrium dependent, and so you have to use things like Le Chatelier with concentrations to change, to push one product versus another. None of those equilibrium kind of concentrations show up in your questions or in the format of an equation. They're all kind of implied that those things are there to allow a reaction to occur. What we're looking at is converting the carbonyl across to that full acetal. In the process, you make a hemiacetal, and so it's just a question of how each of those pieces move through it. As a review, we've got some questions down there which you should be able to nail down. So if we were to look for our nucleophile, the nucleophile is the electron donor in this process. That ends up being our alcohols. We need 2 equivalents of the alcohol to fully obtain the acetal. The electrophile in this process is going to be our carbonyl carbon, and it will be the electrophile all the way through to the end. And for that matter, if we reverse the reaction, that same carbon is an electrophile. If we're going to look at equilibrium, equilibrium is a challenging concept to layer into our acetals, and a lot of that is dependent on all sorts of fun, nasty things. If we wanted to push our reaction to products, we would usually dump in a vast excess of the alcohol to help force the formation of products. The other thing we could do, if you remember Le Chatelier, is remove products. Typically what we would do is try and remove the water. If the water's gone, the reverse reaction can't happen. If we wanted to run the acetal to the carbonyl, we then do the opposite. We would go through and pump in a ton of our alcohol, a ton of our water, and try and remove alcohol in that process to get our product. Okay? As far as speeding the reaction goes, yes, this can be sped up, and really what we're taking advantage of is recognizing, sorry for those pop-ups if you can actually see those, what we're taking advantage of is the nucleophile and the electrophile. If the electrophile becomes more positive, then the reaction goes faster. If our nucleophile becomes more negative, then our reaction goes faster. So to make the nucleophile more negative, you would have to remove a hydrogen, thereby making that a negative oxygen. Now we have a strong nucleophile. To adjust the electrophile to make that more positive, what I could do is take a lone pair of those electrons and share them with a hydrogen. This makes my oxygen positive. It doesn't want to be positive, and so it further polarizes that pi bond, making the electrophile more electrophilic. In the video, we walked through the extent of the electrophile process, or making the electrophile more electrophilic. In this video, we're going to go through and look at how we can make the nucleophile more nucleophilic, and the reason being is that it's easier to look at the nucleophile one to a certain extent, and we'll see why. Okay. We could look at this through energy diagrams. So if we were going to evaluate uncatalyzed reactions versus base or acid catalyzed, the uncatalyzed is going to be a really high activation barrier because you're forming charged intermediates right out of the gate. When that nucleophile first comes in and attacks, you've got that oxygen now losing electrons, so it thereby becomes positive. And then we get that top oxygen gaining electrons, thereby becoming negative. Okay, so we end up with an intermediate that is massively charged. And if we think back to our reactivity of things, charge way drives the energy up high, 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 high. Okay, so that's going to be an exceptionally slow reaction. So what we can do is adjust the barrier by trying to make sure that we don't form such a stupidly high energy intermediate. And what that's going to mean is that we have to nullify one or the other of those charges. If we run under base conditions, what happens is that a negative comes in to attack, which means our oxygen loses that negative charge or loses that positive charge, and we don't see it appear. Under acid catalysis, we end up doing the opposite thing. We protonate, which then means in our intermediate, we don't have a charge there. So we're changing the way the reaction functions to lower that activation barrier and allow the reaction to happen with an appreciable speed. Right? So that's what's happening within those, and our energy diagrams show that. But even then, looking at those energy diagrams, note they're equilibrium. Okay? So any way we do this, this is a back and forth reaction, which does kind of suck because both directions are available. Here's our acid summary. So it goes through all of the gory details behind each of the process. To kind of label this out as a quick review, we should be able to, or by we, you should be able to go through for each step and be like, what type of reaction is this? So this first one, the hint is an acid base. Give you a second to try and work ahead of me. Okay, so you've either paused the video and have now got all the answers, or you're still working ahead of me. Here we have a nucleophile attacking with a loss of a pi bond. This is a nucleophile addition. The next step is just the loss of a hydrogen or a transfer of a hydrogen, so that's an acid base step. The next one is yet another acid base step. The next one, all we've done is broken a bond. Okay, no other formation. So what this is a heterolysis. And then in that last one, we have a coordination. Whoops, second to last one. Coordination, and then the last one is an acid base. So we're seeing lots of acid and base steps to kind of help with those energy diagrams as we move through. The vast majority of the rest of the semester is going to be sitting back and forth on these acid and base steps, and you have to decide when you should be doing it, and that becomes challenging. So first thing to consider, look at your conditions. If you're running under acidic conditions, probably the first thing you need to do is an acid-base reaction where you make it something or you protonate something. If you're under basic conditions, you should deprotonate. Note common pattern within this. If we're running under acidic conditions, we see lots of positive charge. It's because an acid is characteristic for H+. There's the positive. If we switch this to basic conditions, we're looking at something accepting a hydrogen, which means our species had to have a negative charge. So a common pattern that we'll see in our base catalyzed reactions is negative charges popping up. If you're running base and you see acid or positives, you probably did something wrong. If you're running acid and you see negative, you probably did something wrong, okay, as far as your mechanism goes. Last thing I'll say about these mechanistic steps, if you were like, I had no idea what a heterolysis or a coordination was, that's because you didn't reference chapter 7 within the CARDI textbook or look at the not homework assignment that was assigned in the last unit. Again, it wasn't homework, so it wasn't graded, but that's what helped to define what those individual mechanistic steps are. You are responsible for being able to identify them. Okay? With that, let's go through and look at our acetal mechanism where we've tweaked the nucleophile. Okay, this is starting it off for us. I'm actually going to say take a second, pause the video, and see if you can draw out our mechanism to get from the carbonyl all the way down to the acetal. So go ahead and hit that space bar, click, do whatever you got to do, pause it. Make me stop talking. With that, we've got our first arrows drawn for us. If we were to draw out the result of that, we've broken that pi bond. We have a new bond there to our OR. We would have now a negative charge up on that oxygen. Okay. To fully make this into an acetal, or sorry, a hemiacetal, so our next intermediate, we know that we need to somehow get a hydrogen on there. And that does become tricky. So how do we decide to get that hydrogen? Okay. A common question that usually pops up with this is, well, then how can we do that? Because we're in a basic environment. The only thing we've got floating around is OR minus. No, you have OR minus in the presence of HOR, which is our solvent, the alcohol. Anytime you have that active nucleophile, you have that alcohol also floating around. It is present in solution, which means where do I get the hydrogen from? I'm not going to get it from, say, an H+, okay, or H3O+. That would be a bad thing because I'm in a basic environment. Notice the negative. So where I'm going to want to get that hydrogen from is from my solvent. Okay, I would now have the hemiacetal. So how do I then get to the acetal? Right? Well, in the acid catalysis, we just had water come, or our acid come in, protonate that OH, so it was a good leaving group and it could leave. We don't really have that option. Okay? And so if we look at this under basic conditions, we can't protonate. Okay? So how do we get that second OR in there? Well, it's a strong species, so big negative, that would suggest that it should do a backside attack, SN2 style, and just force out the OH. Right? And I would have OH minus floating out here. Right? That's the best mechanism that we could draw for this. But we can't protonate the OH because that would be forming a positive in the negative environment. It's not just going to fall off on its own because hydroxide's not a good leaving group. Okay? So that means it must be forced off by our OR minus. Okay? I did just say something. Hydroxide's not a good leaving group. Okay? That doesn't mean it can't leave. That just means it's not particularly good. Is it okay in this particular situation? Well, that question of okay is evaluating it in comparison to what the solution has in it. The solution has in it OR minus. Negative oxygen, negative oxygen. That may not be a great leaving group, but it's not really unfavorable, okay, as a leaving group. But it's not a great one, so we might say it should favor the reactants. No, we have that equilibrium arrow kind of suggesting that. There's actually another reason why that arrow is actually going to heavily favor the reactants in this case and never form the acetal. Okay? This comes from acknowledging what mechanism this is. This is an SN2 mechanism. In the SN2 mechanism, that little pop-up is super irritating, and oh my goodness, is backside attack. This is a sterically hindered structure. Because it is sterically hindered, that backside attack is very, very unlikely, which would suggest that if we run under basic conditions, we do not get the acetal, and that ends up being true. Okay, when we go through and run the nucleophile tweak, as I'm calling it, we don't get a high concentration of acetals. This becomes great for a multiple choice exam because what we can do is give you the starting material up here, which I quickly erased, and then say, what product do you get? So you'll see the hemiacetal, you'll see the acetal, you'll probably even see the hydrate just for giggles, okay? And I can't think of a fourth incorrect answer at this point, and most people will jump over the acetal because it fits that pattern. But again, the mechanism under basic conditions only forms the hemiacetal. You do not see the acetal formation. Right? If you want acetals, you have to run under acidic conditions, and that's why it went into the play posit, because it's a more relevant reaction. Okay? So why acetals? They are massively biologically relevant. So what we're seeing here, if you haven't taken any biochemistry yet or biology classes, is you are seeing sugar molecules or carbohydrates. Carbohydrates are acetals. So you are responsible in, say, a biochemistry class for being able to identify that acetal location. And it's that carbon that is connected out to our oxygens. Okay? In some cases, you're just looking at a hemiacetal. In other cases, you're looking at full acetals. If I can find one, there we go. For instance, lactose, come on, pen. Lactose is a full acetal because it's connected to oxygen and then that carbon. Okay? You will notice you get some weird nomenclature things that kind of shift with this, and that's coming from biochemistry. Note they've got these kind of bridges, those bends. That bend is because they didn't like the idea of a curved line, so they drew a jagged line or points. Those points aren't carbons, they're the bond turning. Okay? Why do they draw it that way? Because they're biochemists, okay? Or biologists, either way. But acetals are biologically relevant, and when you take biochemistry, you'll end up referencing a lot of aspects behind these and being able to identify the different forms of your carbohydrates. To that end, what lecture on carbohydrates wouldn't be appropriate to bring up our Fischer projections? Fischer projections are carbohydrates. They do form acetals when they cyclize. What we're looking at here at the far right is the Fischer projection of glucose, okay, which is a standard carbohydrate. CHO is an abbreviation for the aldehyde. Okay, and what's happening is that our alcohol comes back and it cyclizes to form that hemiacetal. And that ends up being our cyclic form. So why did Fischer project or draw this odd-looking system? Well, that odd-looking system comes from the fact that if we go all the way back to our OChem knowledge, on the far left, there's a crap tons of wedges and dashes, and it just looks awful. And he didn't want to have to deal with that. So we tried to come up with a system to mitigate that. So this is where Fischer projection rules come into play. And so you can use a Fischer projection if and only if you adjust according to these proper rules. Okay? So number one, orient your carbon chain on that vertical axis. Okay? It has to be always away or dashed. When we look to our far left, the carbon chain is on the vertical axis, but the chain is not always away. So what do we have to do? We have to start changing it so that it's away. Starting at the second carbon, all the way up at the top, you'll notice that our chain is going away. So that position is perfect. The next carbon, the carbon backbone isn't away. So how do we fix that? We rotate a bond to ensure that it gets aimed away. So what happens? As we do that rotation, the location of the H and the OH change across that backbone. We can continue all the way down, and what we see now in that drawing is exactly the Fischer projection. Okay? but no wedges and dashes. Why? Well, there's no wedges and dashes in the Fischer projection because it's a Fischer. We, by default, everything on the horizontal axis must be coming at you, and everything on the vertical axis must be going away. If that's the case, then I don't need to layer in wedges and dashes because it's the definition, right? That allows you to do some interpretations. It gets you R and S potentially faster if you wanted that. It also allows you to throw in other terms like capital D and capital L, which are not R and S, so don't confuse them with that, and I don't want to address it, okay? But those terms do show up in biochem. If you've done the orientation of the three-dimensional model correctly, what it looks like is this. The circle or the structure cycles back on itself, which is interesting because when it cycles back on itself, it starts to bring the alcohol and the carbonyl very close to each other, allowing for the cyclization. All the more reason why Fischer kind of struck on something with his projection, because we can move from that Fischer projection to the, go slowly back to that cyclic formation pretty fast. Okay? So I expect you to be able to look at a biological molecule and identify where the acetal carbon is. I don't expect you to do any of the nomenclature aspects that are associated with Fischer projections or carbohydrates or any of that. I'll leave that to your biochem class. Okay? I think we're good, but just in case, last thing, because we're in organic chemistry, why do we even look at acetals in OChem? Well, we look at it for biological purposes because it's relevant there, but the other reason we use it is that acetals can be used as protecting groups. Remember, we can put them on and take them off relatively easily. And if we go through and look at this reaction, I start with a carbonyl, which would be susceptible to, say, a Grignard attack or a Grignard reaction. If we look at the product, I have an acetal. There's no more polar pi bond, which means no Grignards happen. Right? So if I had a particular structure where I wanted a Grignard to react at one site but not another, I could go on and put a protecting group, right, on the carbonyl as an acetal to prevent chemistry happening there. I'm not talking a whole lot about it. We'll see protecting groups show up at the very, very end of this unit, and we try to minimize the use of protecting groups, and we'll talk, well, I'll just say it now, because if you're using a protecting group, you're adding something to the structure that you're only going to take away. The better method would be to not have to put it on there to begin with. Design a synthesis that doesn't require a protecting group. So be smarter about your chemistry, and then you don't need protecting groups. Okay? The motto of that comes into play with what's known as green chemistry, and we'll talk about that a little bit more when we actually dig into protecting groups. But with that, again, I think we're done. Yep. So we'll do a short video in the next one, but big one here. Apologies, and hopefully that made sense. I left lots of places for you to ask questions, so please feel free to put questions about this lecture into Piazza, because I think everybody would benefit from that, particularly your drawings of potential products.